I don't have any comment. Wow. Let's.
Depends on the baryon symmetry of the universe. So we have we see that if we change the baryon symmetry, then the first peak and third peak will be of the simply perfect will change. So now we have the precise observation of the simply perfect spectrum. As a result, we can have the precise value of baryon symmetry. And of course, baryon symmetry of the universe also determines the large element in the universe, and from that we can also determine the baryon symmetry of the universe. So, and yeah, they both agree very well, and it should be very tiny. So in terms of the so-called baryon to entropy ratio, the baryon by saying baryon symmetry, I mean the difference in number of the baryon and antibaryon, or matter and antimatter. But it is so. From the success of Big Bang nuclear synthesis, we know that this value of baryon symmetry should have been generated in the universe, and the temperature is about then the Big Bang completed. Then the temperature of the universe is roughly 1 MeV. Then the question is that we know that we have the lepton other baryons, reaction baryons. So we would like to know also lepton, how many lepton symmetry in the universe. And indeed, so there are several studies on determining the lepton asymmetry or giving the constraint or upper bound of the lepton symmetry have been done in the study of CD as well as nuclear system. And I think the latest one will be given by Chiral paper in 44 years ago, and which gives that the lepton symmetry in terms of the electrical potential over temperature of neutrino to be 0.001 plus minus 0.015. And so in terms of the lepton to entropy ratio, it is relatively, so it is 4 times 10 minus 1. So that is that. So we know baryon symmetry of the universe is very tiny. In terms of the baryon to entropy ratio, it's 6 times the order of 10 minus 10. But on the other hand, lepton asymmetry is constraint. Just we have the upper bound, and it is around 10 minus 1 in terms of lepton to entropy ratio.
So is it kind of similar to the effective constraint, or?
I think it's not only effective because the existence of neutrino also changes the interaction of the Big Bang nuclear synthesis. So I guess it is mainly comes from the ineffective, but not only ineffective, but the neutrino interaction also matters. Is this correct?
Yeah, it's good. It then also depends on. I mean, you have a chemical potential there, but in principle, you should have different chemical potentials for nu E, nu mu, and nu tau, and things will be different just because it forces the weak rates and the nuclear rates are different. Right? They're less sensitive to psi nu mu than they are to psi nu E because that enters into the weak interaction, right? So
and as far as I understand, this is the constraint on the
this is nu E, okay.
I think so.
So maybe that is the reason. So because if you just talk about an effective, then the constraint is it's not like some percent, right?
Yeah. So I think the same arrow gives this constraint, but I guess this comes from an effective.
I see. So, but then if you include these interactions, then
we have this more stronger. Yeah. Not more, but yeah. But you might know heterogenesis. So the point is that The question is that if we can have the hierarchy between the Lepton symmetry and baryon symmetry. And one hint comes from the so-called electroweak sphalerons. So electroweak sphalerons is a non-particle process coming from the SU2 interaction of the standard model, and that changes the baryon number, the Lepton number, in a way that the NB minus NL to be unchanged, but NB plus NL changes. And it is found that it is very active when the temperature of the universe is much higher than the electric scale. And so this comes from the chiral anomaly of the standard model tells us that the baryon number and the number vibration. So from that, we know that theoretically, if present asymmetry is originated from a process much before the electroweak symmetry breaking, we cannot have larger Lepton symmetry, because if we have too large Lepton symmetry in the universe before the electroweak symmetry breaking, then the Lepton symmetry is converted to baryon symmetry, so that we have too much baryon symmetry. So unless B minus L, B minus L is tuned to be small, we cannot have large Lepton symmetry, so that we will not suffer from baryon overproduction. So let's consider the more in detail. So let's think about the conserved charge in the standard model. So more precisely, so we often say, okay, at low in the present universe, baryon and Lepton number is conserved charge, but we know that chiral anomaly breaks S2 and also U1 chiral anomaly breaks baryon number, and we know only B minus L is conserved. But when the temperature is high enough so that the Newton mass is negligible, so we can have the basis where the electrochemical interaction is diagonal. And in this basis, indeed, not the total B minus L, but flavored B minus L. That is B over B sub minus L is a conserved. And because in the case of baryon sector, the Stoke has two Yuka interactions, so the uptype Yuka matrix and downtime Yuka interaction. Downtime Yuka matrix, and they cannot be diagonalized simultaneously, so that the flavor B is not a conserved quantity, but B sub is a conserved. And also B sub minus is conserved quantity. Then we might think it might be possible that we can, even in the early universe, before the electric symmetry breaking, so the total B minus L is tuned to be 10 to minus 10. But each Lepton flavor asymmetry could be like, or each B sub over LF, B sub minus LF asymmetry could be large. But it is cancelled and tuned to be small. So
maybe you can explain it, but I would have thought that if one of the L, so if one of the LFs is big, right? So you're thinking that the sum of the LFs is going to still be small, but one of the LFs is big. But then wouldn't the sphalerons convert the large LF into B and then the B into the other LFs because it will all equilibrate?
So the point is that imagine if we have large LE and E and the opposite sign of large mu and there on the subject.
Fine.
And in this is the case, and without considering the mechanism I will present, finally around the symmetry breaking, baryon symmetry is changed to be small.
Okay. I mean, I understand. I mean, because there's something that I think I did a long time ago, where you had B minus L exactly equal to 0, but the individual LFs are not 0. and you can still end up with a baryon asymmetry that way.
Yeah, exactly. So this is something discussed by my collaborators, the Kashmir, Kohei Kamada, called the leptoflavogenesis.
Yeah. But we did that about 30 years ago. But that's different because none of them are large. In our case, none of them were very large. So that's why I'm just asking, why doesn't a large LF through equilibrium push you to a large B, which then gets redistributed to the other LFs?
Okay, so the point is that so without taking the possibility to have large lepton asymmetry and large baryon asymmetry from lepton flavor asymmetry is the difference between the washout rate coming from the interaction, right?
Right.
Then and so they could also give so yeah, large lepton asymmetry could give rise to large baryon asymmetry. So large lepton flavor asymmetry could give rise to large baryon asymmetry, and indeed this could give so but such a baryon asymmetry generation is not so effective. So and it as far as I understand, it will give only so if the lepton flavor asymmetry is say 10 to the minus second or so, then the minus 10 baryon asymmetry.
Okay.
So
Maybe go on.
But anyway, I for another mechanism people have not really noticed here. So perhaps we can discuss it more on your consideration. Okay, then so I will also like to comment on the oscillation. So the neutral oscillation eventually was at the asymmetry. So that if we have the total variation total lepton asymmetry, but with flavor asymmetry, then it will be erased around the temperature. The temperature is 10 MeV or so. Then so as a result, so at the time of BBN, lepton flavor asymmetry at BBN is could be calculated from the lepton flavor asymmetry at the temperature higher than much higher here, and it gives so then the neutral mixing angles set of 1,3 is 0. We have this connection, and if the point we have this connection, and we have the constraint that the lepton electron asymmetry in terms of mu over T of C 0.015 or so, and then it will be a bit hard to see, but in the case of theta 1,3, the constraint is in terms of the initial lepton flavor asymmetry to be 0.12, and in the case of the theta 1,3 it is 0.04. So I will refer this value is the present constraint on the lepton observation constraint from the lepton. Okay. Then I will give more stringent constraint on the lepton flavor asymmetry in the early universe before directly integrated by the U1 chiral asymmetry in a similar way that the SU2 chiral anomaly or electric sphalerons give the constraint, the theoretical constraint on the lepton asymmetry. Okay, so this is the kind of prelude, and I will explain the so-called hypermagnetic effect or anomalous transport phenomena recently a hot topic in the hadron physics or condensed matter physics. But I will say I will explain this phenomena, and it's called so-called chiral plasma instability. And in this case, I explained which could be an important role in the RE and then I will okay, let me continue. So I'd like to first talk about the transport phenomena. The transport phenomena is exchange of physical quantity between observed study systems. If we apply some So we have a system, and we apply some external force. Then the media response to give some response. For example, if we have if we add temperature gradient in the system, we will have the heat flow. Or a more familiar case is that the induced energy momentum tensor in the imperfect fluid. So we have the energy momentum tensor for the perfect fluid like this, but we also if the fluid is imperfect, then we would have such a contribution. If so epsilon is the energy density of the system, and P is the pressure density of the system, and U mu is the velocity field, the free velocity field of the system. Then, if we have the gradient in the fluid velocity, then we will have the induced energy momentum tensor known as the shear viscosity and bulk viscosity. In a similar way, if we add the electric current, it is, I think, much more familiar to you, but if we apply an external electric field in the media, then the Ohm's current runs. And so it could be understood as the induced current of the electric field. So like this. So and we know that electric conductivity. And indeed, from the consideration of the hydrodynamics as well as and you can look at you can read this explanation by Landau-Lucy's textbook on the fluid dynamics. But we know that if we apply electric field, we need the electric current one, and it could also the electric current parallel to the temperature gradient or the density gradient is also run, but it happens to be the same constant. Anyway, it is a very long graph, but we have a question. If we know that if we apply an electric field, electric current run. However, if we apply magnetic field in the system, is electric current run? The answer is no for usual media, because parity doesn't allow. So parity flips the electric current and the electric field. But the magnetic field is parity. So we cannot have the electric current to magnetic field if the system doesn't have any parity of the quantity in the system. But we know that we can have a media that is chirality. So if the system is consists of fermion, we have right-handed fermion and left-handed fermion. And it responds differently to for the spin and momentum correspondence is different. And as a result, we can add so as long as as in the limit we neglect the chirality interaction by mass term or the helical interaction, the chirality is a conserved quantity, so that we can define the chemical potential for right-handed particle and left-handed particle. And the difference between the right-handed and left-handed particle is a capacity of the code. As a result, so the magnetic effect is found, so that the electric current parallel to magnetic field and proportional to chemical potential. This has been indeed found by Vilenkin in the cosmological context in 1980, but its application hasn't been studied very well. And time passed, and in 2008, in the context of hadron physics, Kamada and Fishman and Weininger found that in the completely different context. At that time, they didn't notice that. When they wrote that paper, they didn't notice the being paper. But anyway, hypermagnetic effect is now found to be found to exist. And indeed, it has been understood as related to hypermagnetic. So we can see it by looking at the random data. So imagine we apply a magnetic field in the direction or the direction. Then we will have the random data. And the interesting point is that right-handed particle has the momentum parallel to the spin. But the left-handed particle is the momentum and the parallel to the spin. As a result, the lowest random level is opposite for the right-handed particle and left-handed particle. Then, if we have parallel chemical potential, so that the right-handed particle has a mu5 half as a chemical potential, and the left-handed particle has minus mu5 half as a chemical potential. As a result, we can see that the charge E particle is occupied up to here, and then the hole is occupied here for the left-handed particle. And you can see that the positive charged particles have the plus V direction, and the hole, so it is anti-hole. Hole has also the negative direction, but its energy is negative, so it contributes to the opposite current, and as a result, so as a particle current, there are no current, but we see that the electric current is induced to the magnetic field. So we can see that for one state, random generation factor gives this number density of the system, and then we have the current up to here, so that it gives it gives proportional to mu pi. So it gives the current proportional to mu pi and proportional to mu pi and parallel to 2. And we can easily understand that it is related to chiral moment. Because if we apply electric field in the same direction, the direction, then this state is accelerated to this one, and this state is accelerated to this direction, so that the difference in the number of right-handed particles and left-handed particles becomes larger and larger. And by calculating the occupation number, we see that the Pn5 over dt is scale times magnitude. And we know E dot B is minus FF0. So we reach at the well-known chiral manipulation. Is that clear?
What is the 5 referring to?
5 is the chiral. So 5 is mu r minus mu m.
Oh, okay. Why 5?
It's gamma 5.
Oh, okay.
So sometimes it is also written as A, so mu A axial.
Okay.
But it is more popular to write mu pi, coming from gamma 5. So then I hope you are convinced that in the chiral medium, if we have the chiral asymmetry in the system, then if we apply magnetic field in the system, then electric current parallel to magnetic field. It is a bit strange, but yeah. And the condensed matter physicists try to find it experimentally in the so-called wire semi-metals. So in the wire semi-metals, artificially one can manage so that the non-color spectrum in the system with the corresponding system, and then they are about to have the 5 sigma confidence level of the anomaly. Anyway, and then so I explained I hope you are convinced that anomaly effect really occurs. Okay. Then let me talk about the so-called chiral instability. So immediately after we know that such an induced current exists, we can rewrite the Maxwell equation in the MHD. So Maxwell equation is the Faraday law and Ampere's law. And Ampere's law should include E dot term, but or displacement. But here I consider the system in thermal plasma, so that so that electric field are split, and as a result, E dot is negligible. Then, but E dot is negligible, but we still keep E there. And in a fluid, the Ohm current is not just sigma E, but we have the Lorentz constant B plus E. Yeah? But this is the Ohm current. But if we have chiral asymmetry in the system, we have the chiral magnetic effect, the current induced current coming from chiral magnetic. Then from Ampere's law plus this electric current expression, we can rewrite E in terms of B and mu pi. Then substituting E from this to this Ampere's law, we reached out to the equation notion for the magnetic field. And then, so we performed, we decompose magnetic field in terms of circular polarization mode plus minus. And circular polarization mode is the eigenstate or eigenstate for the rotation operator. As a result, we have rotation here, and then so the equation motion becomes the usual dissipation term coming from the Ohm's current plus the contribution from current magnetic field. And if we have the fluid, we have the fluid velocity dependent term also. Anyway, so from that we can see that if, for example, if we have positive mu phi in the system, then small k this term overcome this term. And then so without chiral magnetic effect, magnetic field just decays exponentially, but chiral magnetic effect gives rise to the exponential amplification of magnetic field. It's clear? Okay. Then, so if the fluid velocity is negligible and mu phi is kept constant by, as I said, by helicity mode of the hypermagnetic field instability, like this. So the K, so there is a typical K wave number defined by this condition, so that alpha y over phi. And then, so the other result, maximally hopefully hypermagnetic field are generated. And one comment is that okay, so we know that this is coming from the anomaly equation. So we have this one, but the idea is not to be the total derivative term of the Chern-Simons current. Other that we can rewritten. So I would say we could say that the chiral anomaly is not the process to chirality by violation of chirality, but we can extend the conservation law of the chirality plus magnetic. And that is that. So this process could be understood as the transfer from the chirality to magnetic helicity. Once we appropriately take into account the reaction to the dynamics of the chiral asymmetry.
Sorry, is H invariant?
Good point. So of course the helicity is not gauge invariant, but with the appropriate boundary condition, the derivative of helicity is gauge invariant. Is it correct?
Yeah, I mean, you can express this by Y12 by the total derivative, but in that case, the current is not gauge invariant, right?
The current itself is not gauge invariant, but the derivative is gauge invariant. Derivative is gauge invariant, and so we can, in the sense, so the Q5 and H itself does have appropriated is not gauge invariant.
Yeah, that's what I wanted to ask.
But the change of Q5 plus HY is gauge invariant.
Okay.
Sorry, in a cosmological setting, how do we know when the velocity is small and when is it not small?
So it depends on the cosmic history. So if we one possibility is that if very weak process could generate quietly produce the mu5, then we would imagine that there are no velocity at the initial function. But we could also consider so in that sense at present the consequence of this instability should also depend on the initial velocity field. But at then the point is that recently, it is already 5 years ago, but the numerical MHD people got interested in this process and they performed the numerical simulation. And then they confirmed the complete conversion from the color asymmetry to magnetic field. So you can see that this is magnetic field and this blue line represents the magnetic field. So as Kohei pointed out, it's not gauge invariant quantity, so they gave an kind of gauge fix. But anyway, and then so the and purple line represents the red line represents the chemical potential. And then so this dashed line represents the velocity. And at the first time, so they started from the relatively small velocity field. And then at that time, velocity field is negligible, so they see that the exponential growth as predicted. And at some point, velocity field becomes no longer negligible. But the instability still continues, so that the total magnetic helicity is the one predicted, the maximum helicity is realized. Is predicted from the color asymmetry. And then the color chemical potential is found to be started to decay. And other with some explanation is that the free energy carried by color asymmetry in fermions is bigger than the free energy carried by helical magnetic. So that the transfer, the system will not go to the equilibrium of the magnetic helicity and the color chemical potential, but the complete transfer will be bigger. And it is indeed confirmed by numerical energy. So we have such a but due to the box size, they do not see the complete erasure of mu5. But from this conservation, we have such a schematic picture of the evolution of magnetic field from the current field.
So how do we know the asymptotic state is not reach certain equilibrium between the chiral asymmetry and magnetic helicity? Why do you say the chiral asymmetry is going to be eliminated?
So the point is that
their study, I assume, includes they saw the whole system, so they included the feedback effect. So so in essence, I don't know what's my endpoint. My endpoint might well be that I have some residual chiral asymmetries and have certain large fraction of magnetic helicity.
The point is that the free energy carried by magnetic field is given by the helical magnetic helicity times its typical wave number, and then the free energy of the fermion is color chemical potential squared temperature squared. Okay, then but due to the hydrodynamic effect, the wave number of magnetic field becomes longer and longer. as the decay becomes smaller and smaller. And in this study, it has a box side. So there is the upper bound of the length scale, so that it cannot. So the free energy of magnetic field cannot become zero. As a result, we find the chemical potential, so the free energy carried by fermions does not become in this chemical situation. Does it answer to your question?
Sort of. Okay, thanks.
Then we would wonder if the color asymmetry can follow. So we know that the chirality is broken down by interaction or mass transfer. So we wonder if such a process can take place in the animal. The point is that something related to the fact is 1991 you said that well, I think 93 I remember, but with these journalists and cameras, so that the sphalerons washout complete and the electroweak.
Right.
And so the point is that the electroweak is in equilibrium within the temperature 10 to 50 dB, and then but other Yuka interaction also has a temperature. For the so in the Yuka interaction, the rate is proportional to the temperature, so that lower temperature Yuka interaction is equilibrium. And then so electron decoupled is in equilibrium 10 to 50 dB. Up Yuka becomes lower than 10 to 6 dB. Down Yuka, strange Yuka, mu Yuka, like this. And we have topical here and strong sphalerons and weak sphalerons. And so we often say that conserved charging of the standard model is flavored B minus L. And at that time, mu5 is not a conserved quantity and zero. But this is true only when the temperature is lower than the 10 to 50 and the electron Yukawa is in equilibrium. And so we have several interactions, but so we so the one interaction in equilibrium, one conserved quantity disappear and so on. So that then just for convenience, we divided the region like that. The point is that at the high temperature interactions are out of equilibrium, like as I said. Then for the 10 to 5th to 10 to 7th GB, the conserved quantity of the universe is flavored B minus asymmetry and right-handed electron number. And at the temperature is 10 to 6 to 10 to 9 GB, down Yuka and up Yuka are also out of equilibrium. As a result, we have two other conserved quantities. And it is for our convenience, we choose the conserved quantity is right-handed electron number and the right-handed up minus the difference of right-handed up and right-handed down. And also the 2 times the baryon number carried by first generation minus the baryon number carried by second generation minus baryon number carried by third generation. Becomes the conserved quantity. So we can identify the conserved quantity, the number of conserved quantity by checking how many Yuka interactions are in equilibrium. But the point then the interesting point is that we can calculate the as Tanaka-Habib's way, we can determine the potential for each particle as well as the chemical potential. And we find that the chemical potential in this temperature is that the linear combination of the chemical potential for the right-handed electron and flavored B minus L asymmetry. At high temperature, we have other conserved charges, but somehow accidentally the 2B1 minus B2 minus B3 does not appear, but mu5 is given as the linear combination of the right-hand electron chemical potential and UD minus U minus D chemical potential and the flavor calculation. Then, okay.
Sorry, the constraint that you mentioned at the beginning and also written here, I think in this slide, is about the vector charge, right? Like this, you mentioned like a 4 times 10 to the minus 3. So there's a constraint coming from, for instance, BBM, right?
Yeah.
So that constraint is on the vector charge, right? Not the actual charge. Or maybe I misunderstanding. So I'm just wondering.
This is just the constraint for the electron neutral chemical potential.
So electron chemical potential means that it is a vector one, like.
In that sense, we focus on just neutrino, so it could be it will be understandable. We have large neutrino asymmetry, then only we have right-handed neutrinos. Large, so it's axial.
Okay.
Right. Anyway, so then imagine for large lepton flavor asymmetry, which is E minus LF over T is theta minus second, and we satisfy with the not much D minus. Then the generally it gives large Chiral asymmetry like this. Then we know the how CK grows, so we can determine each temperature the chemical instability grows. And for such a large new chemical potential, the temperature is 10 to 7. Then, so before the growth of plasma instability, so and imagine that the new right-hand electron and also the U minus D chemical potential is vanishing. Then the mu phi is determined by the mu delta. I just know I only see one balancing. But then once plasma instability grows, I said there will be a complete conversion from the chemical potential to the magnetic helicity. Then magnetic helicity is generated here, and but at the same time, this process doesn't breaks individual Chiral anomaly for the anomaly particles, so the right-hand electron as well as the U and B will be generated. But then, as a result, the magnetic helicity, helical magnetic field with the helicity is given. It will be generated. Then, what happened in the Fermi spectrum? So in this process, the favored B minus L is a conserved quantity, so it conserved up to BBN and the neutral station. But the right-hand electron number is no longer conserved when the temperature becomes below 10 to 50 dB or 10 to 10 at 100 dB, and then determined by the number determined by the multiplier. And B minus L and mu B and mu L is distributed by sphalerons, so that it gives very small one. It will be one expectation. So as Keith mentioned, there could be a partial conversion, but let me omit that. Then, but the interesting point is that something I found with Andrew Long at the Rice University when he was I was in Arizona State University and he was at Chicago also. But the point is that when the elevation is breaking, the high magnetic helicity carried by hypergauge field becomes to the helicity carried by helicity carried by electromagnetic field. At that time, we know that from the anomaly equation, delta P equal to delta L equal to the delta H by the change of magnetic helicity, change of hypermagnetic helicity minus change of the Chern number of the vector. And at that time, so the magnetic helicity carried by hypermagnetic helicity converted into the electromagnetic helicity. That electromagnetic helicity is a combination of the original hypermagnetic helicity and the SU2 chance number carried by the third component of the SU2. As a result, we will have the baryon symmetry generation due to the conversion of hypermagnetic helicity to electromagnetic helicity. Of course, this process does not break B minus L, so that this baryon symmetry could be offset by electric sphalerons again. But it is the competition between the how electric sphalerons freezes out and how the electric integrating completes. And as a result, we conclude that the relatively large baryon symmetry is generated with this equation. So if we have hy to be the 10 to the minus second is cubed, it gives baryon to entropy ratio to be 10 to positive, 10 to the minus positive. So this concludes that if the chiral plasma instability grow before the temperature is 10 to 60 degrees, and the electron nuclear interaction goes in equilibrium, so that means it becomes zero. So then the electron nuclear, then the baryons are open. So it is, I would say it is analogous that the large electron asymmetry before this electricity breaking for bits to have an electron asymmetry before the electricity breaking, we conclude that so SU2 chiral anomaly for bits to have large lepton asymmetry, U1 chiral anomaly for bits to have large lepton flavor asymmetry in the aluminum. So compared to the aluminum constraint, so we conclude that the chiral plasma instability should not grow before the equilibration temperature 10 to 100 degrees. So that side of the chiral asymmetry is this. And so we have the constraint from this constellation that the lepton flavor by lepton flavor asymmetry. A flavor B minus L asymmetry should be smaller than for time 10 to minus 1. As I explained in the first part of my talk, the lepton flavor pair asymmetry is conserved by the lepton 1 or 1, so that this our constraint is 10 to 100 stronger than the previous. Okay, so let me summarize my talk. So, we conclude that flavor asymmetry is not allowed at temperature before the electron nuclear equilibration, 100 dB, due to the baryon overproduction, even if the total P minus L is vanishing. The process is that if we large lepton flavor asymmetry, then it corresponds to the large chiral asymmetry in the plasma. Then large chiral asymmetry induces so-called chiral plasma instability. As a result, we will have the large magnetic field with large magnetic helicity. Then large magnetic helicity is converted to baryon asymmetry as the electricity break. So this is the mechanism that we have. And it is similar to the large lepton asymmetry is not allowed before the electricity breaking due to baryon overproduction by the electric sphalerons in the over the SU2 chiral anomaly. The hyper U1 chiral anomaly for this to have large lepton flavor asymmetry at the temperature 10 to 100. That's all. Thank you very much.
So is it fair to call it a bond if, let's say, the dilution that could happen after the electroweak phase transition could put the baryon symmetry in the right amount, right?
Yes,
so
it is possible, but it is came to the case of the Lepton large Lepton symmetry converted to the sphalerons. To the baryon symmetry.
So yeah, with dilution, then this
Yeah,
bound.
that
should be-
is dilution.
Okay.
Dilution is here. Yeah, and yeah.
So you're producing a baryon asymmetry around electroweak symmetry breaking here. I thought the usual story is that the like out of equilibrium condition for electroweak baryogenesis means that you would need like a first order phase transition. Does that mean this is happening as like a first order phase transition?
So it is a crossover. We are seeing crossover. And this estimate is given from the latest study of in light of the 125 GB. And the essence is also sorry I didn't explain much, but in this mechanism, so the vibration is provided by the chiral magnetic, and we have I didn't explain explicitly, but the magnetic fields are generated, and magnetic fields are not in equilibrium. So they are not they evolve
Oh,
out of equilibrium process. And the magnetic field carries magnetic helicity. It means that chirality. So the Taurus condition
is like they're not in equilibrium because like one helicity is not equilibrated with the other helicity,
is. So
like because you have one of more helicity.
in this process, the essence is that the magnetic long range. So I didn't explain that long range magnetic field. And long range magnetic field for the hyper field. We have long range magnetic field for the electromagnetic. And this process and this magnetic field is not in equilibrium. So even though the other part of the universe is some equilibrium, but magnetic fields are not in equilibrium. So the Taurus it doesn't conflict with the Taurus equilibrium.
It's kind of a related question, but could you explain, maybe you mentioned, I missed it, but could you explain again why these large helical hypermagnetic fields are not erased? Like, this magnetic helicity is not erased because even after electron equal interaction is in equilibrium.
Yeah, so the point, the point is that when I could write. So we could write delta H, and it's not really invariant. So but pretty solid. Forgive me. So HY is given. So HY is written as y dot dy. Right? Then we have delta HY is we have this equation. DTHY is the DTNP. From the chiral. Then, and DTHY is now given by by dot B, but it could be written as lambda. So let me write the over. We can write KB square, but here we have the mixing up. So in the definition of in the definition of
I think I'm not talking about this baryon production. I'm talking more about the, before the, so what you said is that before the electron interaction is in equilibrium, what is conserved is like the linear combination of the Q5E and this hypergauge, right? Helical magnetic helicity, right? So that is conserved.
Yeah.
And then, if you have this initial, asymmetry in this electron sector, then you generate this, magnetic helicity. That's what you said, right? If I understand correctly. But then once you have the electron interaction, this linear combination is no longer conserved, right?
Yeah.
So that means that in principle, you can also erase this linear combination by using this electron interaction. And that, I assume, kills this, magnetic helicity. But it seems like you're saying that that doesn't happen actually.
Yeah.
And,
So
I'm just wondering why.
Flavored Lepton asymmetry is conserved, even though and mu phi becomes zero, and the electron is in equilibrium.
Yeah.
But the helicity is not magnetic field is now long range, and they do not care about the microscope process.
So it's more about the scale difference, you mean?
Yeah. So the HY magnetic helicity is becomes conserved quantity as long as the such a process takes place.
Okay. So in principle, it is not conserved, right? In a strict sense, but you're saying that you know.
So okay. So magnetic helicity is not conserved quantity, and magnetic helicity decays due to the from the Ohm's current. And so now we describe the magnetic field in terms of the magnetic hydrodynamics and the long range effective theory. In this picture, the decay of magnetic helicity is driven by the Ohm's current. And then but we can estimate the time scale of the helicity decay due to the Ohm's current, and it is much longer than the evolution.
So you have to really check the time scale, and then you can just say that the time scale is slow compared to.
Yeah. And yes, as a result, in MHD, magnetic helicity is not the exact conserved quantity, but for ideal MHD, where the electric conductivity is large enough, the magnetic helicity is almost conserved quantity, and in user case, for the pen the magnetic hydrodynamics is a good way to describe the evolution of the system, then the magnetic helicity is well conserved.
And do we have observational evidence that such long-range magnetic fields exist? Do we have observational evidence that such long-range magnetic fields exist, for example, in intergalactic medium?
Yeah. So thank you, perhaps you I don't know if you have already seen my appendix. So the evolution of magnetic field can be extrapolated from the cosmological image studies, and so this is the point is that there is a kind of claim that there could be a magnetic field in the intergalactic void. That is, so the idea is that so we are here, and we know that the astrophysical object called the blazars, and blazar is an object with high energy photons, and it could be around 1 keV. But for them, and it is a cosmological scale like 100 megaparsec scale. But the galaxy body is not completely empty, but there is photons from the stars far away. As a result, the photon from blazars and photon from visible photon from the stars will be annihilated in the produce diffracting line pair. Then we also have the CMB photon. Then we see the cascade photon, the scale of G. If we see blazars and TP, actually these photons should be converted into the GB cascade photons. Then the TB scale gamma observatory such as HES has identified this such as blazars, and Fermi tried to see this GB cascade photon, but they didn't see. Fermi didn't see the GB cascade photon. And one explanation is that if we have magnetic field, then the trajectory of Eclat and the electron positron are bended, and GB cascade photon goes otherwise to us. So this would explain the absence of the GB cascade photon. From this consideration, the Fermi people give rise to the lower bound of the integrated magnetic field. And so the physical region is the sensitive region from the blazar observation. And in our study, tells that baryon asymmetry, in our study, baryon asymmetry is explained with the magnetic fields with this, right? So the observed magnetic fields predicts baryon overproduction already. So I would say this magnetic fields, integrated magnetic fields, suggested by laser observation, is a kind of foreground that has been generated much after electricity breaking. And then, in order to test our scenario for the baryogenesis, so it could be also, I explained the baryon production, but with tuning, the baryon could be also baryon asymmetric, the baryon asymmetric could be explained. So, in order to test this scenario, we need to remove the foreground magnetic. So it will be very hard topic, I think.
Yeah. So you mentioned that can you go to the summary slide? You mentioned that you put a constraint on the Lepton flavor asymmetry, but in principle, you also put a constraint on the chiral asymmetry directly, right?
Yeah,
So
yeah.
why is it that you focus on the constraint on the flavor asymmetry instead of just the chiral asymmetry?
So our constraint is general constraint for the mu5. So yeah, one issue is that my Japanese colleague recently claimed that helical dance is different, and perhaps given not agree that point for helical dance problem and
Oh, yeah.
So yeah, so for the conservativeness, I just use this is the constraint, but people could believe, people could be serious on the helical abundance anomaly, and then we could ask for the large Lepton flavor symmetry to be the origin of the helical abundance. But the possibility is not.
But there is no anomaly.
Yeah. So my collaborators consist of many Japanese. So, so the groups who claim helical anomaly is also universal talking.
Are they still claiming?
I'm sure I have not had the contact with them.
Because I don't think the paper's been published, and I think they were told what the problems were.
Okay. So all sample. So the first author is Matsumoto, and he is, I think, the second year master course student, and then I think he's provided by Coach. So that the paper also Kawasaki was in the paper. How Kawasaki-san is serious.
I think he just didn't know.
All right, more questions?
I have another question, but maybe it's a bit too technical.
Okay, let's send this people.
So about this, you said that the chirality is mostly transferred into the gauge sector, right?
Yeah.
In this estimation, but this system is very similar to the Asymmetry equation case, right?
Yes.
And in that case, that there are some studies, for instance, by Kohei and so on, like including axons and gauge fields and also fermions. And in that case, sometimes they say that you produce more fermions than gauge bosons in the end, right?
Yeah. So in such a case, the chiral anomaly is not violated. So the chiral asymmetry